So for a discrete random variable x, the cumulative distribution function we should define. First of all, before looking at the complex mathematical equation here, please notice the word. It says cumulative distribution function. Cumulative. Cumulative means what? Cumulative means aggregated. So in the probability mass function, we were indicating the probabilities. In the cumulative distribution function, we are going to aggregate this probability. So we are going to add them up. So this function gives us summation of probabilities up to a point. So let's read the explanation, mathematical expression. First of all, a cumulative distribution function is represented with capital F of x. And this x here is again an arbitrary real number, just like in the probability mass function. And this capital Fx represents the probability of our random variable to take values less than or equal to x. Unlikely to the probability mass function, remember, the probability mass function was representing the probability of our random variable being exactly equal to a certain value. However, the cumulative distribution function gives you the probability of our random variable to be less than or equal to a certain value. So we are going to sum up all possible probabilities of our random variable for values which are less than or equal to x. Okay? So how do you determine that? By this summation. So it says you need to sum up the probabilities for which I is less than or equal to x and the probabilities are positive. So we need to sum up all positive probability masses for I which are less than or equal to x. So this is called cumulative distribution function, which means you are running down the list of probabilities in a cumulative version rather than indicating the probability masses one by one. You are writing them down in a cumulative version. So this function specifies for all real values of x from minus infinity to plus infinity, you choose any arbitrary x, and for that x value, it gives you the sum of probability masses for which the values are less than or equal to x. And just like the probability mass function, the cumulative distribution function also has an abbreviation, which is CDF. So when we say CDF or PMF, you need to understand what type of function that we are talking about. So learn the abbreviations. PMF stands for probability mass function and CDF stands for cumulative distribution function. Now, let's just say we have a random variable x, which can take 4 possible values starting from 1 to 4. And these values can be taken by these random variables according to these probabilities. This is the probability mass function of our random variable x. The question gives you this. Write down and draw the CDF of x. Now, my friends, according to the definition of the cumulative distribution function, we can actually determine it by looking at the probability mass function. In fact, there is a one-to-one relationship between the probability mass function and the cumulative distribution function for discrete random variables. So if you know the probability mass function, you can calculate the cumulative distribution function. And if you know the cumulative distribution function, you can determine the probability mass function as well. So how do we do that? This is the answer, but I'm going to explain it to you. Imagine you are moving from minus infinity to plus infinity here. Okay, you are moving forward from minus infinity to plus infinity. And at 1, 2, 3, and 4, we have 4 probability masses. So imagine the plot diagram of this probability mass function. Remember now, as you move this lowercase x from minus infinity to plus infinity, as you move on the left-hand side, some probabilities will accumulate. Until you reach 1, there will be no accumulated probability, 0. But when you reach 1, the total accumulated probability will be 0.25 because there's a probability mass at 1. And it is going to remain the same until you reach 2 because there is not any other probability mass up to that point. So between 1 and 2, the total accumulated probability mass will be 0.25. But when you reach 2, when x is equal to 2, the total accumulated probability will reach to 0.75. And it is going to remain the same at 0.75 until you reach 3. And when you reach to 3, the accumulated probability will be 0.875. And it is going to remain the same until you reach 4. And when you reach 4, the accumulated probability will reach to 1. And it is going to remain at 1 until infinity. Because after 4, there is not any other probability mass. Or in other words, let's describe this cumulative distribution function in the terms of definition. So I have told you that a cumulative distribution function is the probability of a random variable to be less than or equal to an arbitrary x. Let's just choose x as 2.5. So I am asking you this question. What is the probability of my random variable to be less than or equal to 2.5? By looking at the above function, you can say that the probability of a random variable to take values less than or equal to 2.5 are 0.25 and 0.5, which sums up to 0.75. So there are only two possible values under that. You can answer the same question by directly looking at the CDF. What is the probability of my random variable to be less than or equal to 2.5? You need to check in which interval 2.5 is. 2.5 is in this interval. And my answer is 0.75 again. So I am asking you this question again. What is the probability of my random variable to be less than or equal to 3? You can answer this question by looking at the probability mass function and sum up these three probabilities. You can say it should be 0.875 if we sum up these three probabilities. However, you can answer the same question by looking at the CDF. What is the probability of my random variable to take values less than or equal to 3? So this means this lowercase x is 3. And when this lowercase x is 3, the answer is 0.875. Now, my friends, the next step is to draw this CDF. And in this picture, there is the drawing. Now check this out. I am going to move between the pages in the following explanation. So it says when x is less than 1, the function yields a 0. When x is less than 1, the function gives us a 0. When x is between 1 and 2, where 1 is included but 2 is not, the function gives us a 0.25. The function gives us a 0.25 when x is between 1 and 2, and 1 is included but 2 is not. So when x is between 2 and 3, 2 is inclusive but 3 is not. In that case, the function gives you a 0.75. When lowercase x is between 3 and 4, 3 is included but 4 is not, the function gives you a 0.875. So when the x value is between 3 and 4, 4 is not included, the function gives you a 0.875. Finally, when x is greater than or equal to 4, the function gives you a 1 until the infinity. So as you can see, the cumulative distribution function for discrete random variables is a stair-shaped function. And please notice that this is an important point, my friends. So at each value that the random variable can take, which are 1, 2, 3, and 4, there is a jump, right? At each value, there is a jump. And the size of these jumps, if you check the size of these jumps, are the probability masses. So the probability of our random variable to take the one value is 0.25, the jump size here. The probability of our random variable to take the two value is 0.5, the jump size here. The probability of our random variable to take the 3 value is 0.125. And the probability of our random variable to take the value of 4 is again 0.125, which are respectively the jump sizes here. Okay, so this means what? By determining the jump sizes here, you can also calculate the probability mass function looking for, at a CDF. So instead of asking the CDF in this question, if I give you the answer and ask the question, you can also compute the probability mass function from the cumulative distribution function, right? What are the properties of a cumulative distribution function? So what type of typical aspects do we observe in cumulative distribution functions? First of all, my friends, a cumulative distribution function for discrete random variables is a non-decreasing function. Now, you can check this. Because it goes cumulatively, because the probability masses cannot be negative, this function never decreases. At the possible values that the random variable can take, it is going to increase, but at other values, it is going to remain constant. And whenever it reaches to, again, another value that it can take, again, it is going to increase with a jump. And in the end, it is going to reach to 1, because the sum of all probabilities equal to 1 for a discrete random variable. So because of that reason, this function is a non-decreasing function, we say. It sometimes increases with positive jumps, sometimes remains constant. And it is a stair-shaped function. As you can see in this example, it is a stair-shaped function. So we can call it is a piecewise constant function in the form of a stair. And we can prove that it is non-decreasing. How? Remember, in the axioms of probability, we have mentioned about a concept. We have said that in the same sample space, if we have two events, one of which is a subset of another, then the probability of the subset should be less than or equal to the probability of the covering set, right? Now imagine this. We have two arbitrary A and B values such that A is less than or equal to B. The event of X being less than or equal to A is contained in the event of X being less than or equal to B. Because of that reason, this event is the subset of this event if A is less than or equal to B. By the axioms of probability, we should say that the subset of an event should have a less probability than the probability of that event. Because of that reason, FA will be less than or equal to FB, which will indicate that a cumulative distribution function can never decrease. And because the sum of the probabilities are equal to 1 in a probability mass function, the left limit of a cumulative distribution function will be 0, and the right limit of it will be 1, which means, my friends, this cumulative distribution function will always start from 0, and it will reach to 1 in the infinity. Okay, at minus infinity, it will start from 0, and at infinity, it will reach to 1. These are the important properties of CDF. Now, we solve a question about the CDF concept again. We are going to toss two fair coins, and we will denote Y as the number of heads appearing. Actually, we have already calculated the probabilities of Y to take on these different values. The question tells us this time we need to write down a formal definition for the probability mass function and the cumulative distribution function of Y, and we are also going to draw these functions. Okay, so we have already solved this question. You know that random variable Y can take 0, 1, and 2 values. This is the probability mass function here that we need to define. By the way, at this point, you can realize that the random variable is labeled with capital Y. However, the input of the function is X, but it doesn't matter. Okay, I mean, this is just an input of the function. This input indicates that if the input takes 0 value, the result is 0.25. If the input is 1 or 2, the results are as follows. And if the input is anything else, it is 0. So the input can be another letter, but the random variable can be another letter. It doesn't matter, my friends. And the cumulative distribution function can be written in the cumulative terms again. So in this page, at page 25, we have the plot diagram of the probability mass function here. Now let's check it. As I move from minus infinity to plus infinity, let's calculate the cumulative probabilities. So until I move 0.0, there is not a cumulative probability. So the cumulative probability is 0. Now, when I reach to point 0, the accumulated probability becomes 0.25. And even if I move forward, the total accumulation will not change because there is not any other probability mass up to this point. As you can see, as I move from 0 to 1, the accumulated probability or the cumulative probability does not change. But when I reach to 1, the accumulated probability will become 0.75, which will remain the same until I move to 2. And when I reach to 2, the cumulative probability will become 1. So as you can see, again, we have a stair-shaped function, which is non-decreasing, and that starts from 0 to infinity. You can also write down this function. You can say that for x values which are less than 0, the CDF is equal to 0. For x values which are between 0 and 1, 0 is included, but 1 is not. The cumulative probability is 0.25. For x values which are between 1 and 2, 1 is included, but 2 is not. The accumulated probability is 0.75. And finally, for x values which are greater than or equal to 2, the accumulated probability is 1. So this is the plot diagram of the CDF. My friends, you need to understand the relationship between a probability mass function and a cumulative distribution function. If I give you one of these, you should be able to convert it to the other one. Okay? So from here, by accumulating probabilities, you can compute the cumulative distribution function. From here, by looking at the jump sizes, you can determine the probability masses. That's as easy as it can be explained.